Okay, for this part, we are looking into area of surface. And regarding area of surface, and this will tie in by and large to what we had from the determination of the length of a curve. So we have the area of surface of an object. So we have, first of all, for an object revolved about the x-axis. And now for the area of surface of an object revolved about the x-axis. Okay, and we can say that we have going from, in terms of integrating with respect to x, so we can say we have going from a to b of 2 pi times the function f of x, and we have times, okay, the square root of 1 plus the square of the derivative, dy over dx. Then we have dx, and in special cases, if you're looking at integrating with respect to y, so you have, in this case, you have going from y is equal to c to y is equal to d, so you have 2 pi times the projected radius and in this particular case, so we have 2 pi times the projected radius. And since we're looking at integrating with respect to y, so we have 2 pi times p of y, and we have times the square root, and we have 1 plus dx over dy quantity squared dy. Now, in the case of the area of surface of an object revolved about the y-axis, for the area of surface generated about the y-axis, so going from c to d, and we're going to have 2 pi times f of y, and we have times the square root, and we have 1 plus the square of dx over dy quantity squared dy. And if I were to put this in terms of integrating with respect to x, so I have going from x is equal to a to x is equal to b, and we have 2 pi times the projected radius, p of x, and I have times the square root, and I have 1 plus dy over dx quantity squared dx. And let's say that just for starters, say if I were to determine the area of surface generated about the x-axis, and I'll just say that I have y is equal to 2x from x is equal to 0 to x is equal to 2. So we have, in the case of illustration here, So I have 2, 4, 0, 0, 2, 0. Okay. As the corner points. Okay. Now, in taking what we have here, so if I'm looking at integrating with respect to x, okay, so I have, in this case, I have y or f of x is equal to 2x. Okay, and I'm looking at the area of surface. And I have generated about the x-axis. Okay, now for the area of surface generated about the x-axis. So again, I have integrating from a to b, and I have 2 pi times f of x times the square root of 1 plus the square of the derivative dy over dx. And just to start us off, okay, so again we have with y, okay, so y is equal to f of x is equal to 2x, taking the derivative. So you have dy over dx is equal to 2. And we have for the square of the derivative, okay, that is going to be equal to 4. So in going back in the determination of the area of surface generated about the x-axis. So I'm going from x is equal to 0 to x is equal to 2, and we've got 2 pi, and again your f of x is going to be at 2x, so I have 2 pi times 2x, and I have times, okay, the square root, and we have 1 plus the square of the derivative. So I have 1 plus 4 dx. So I have going from 0 to 2. And here I have 4 pi x times the square root of 5 dx. And taking the antiderivative. Remember, antiderivative of x is going to be x squared over 2. And multiplying by 4 pi and the square root of 5. So I'm going to have 2 pi x squared times the square root of 5 as x goes from 0 to 2. And for the area of surface, I got 2 squared is 4 times 2 pi times the square root of 5. So we end up at 8 pi times, okay, the square root of 5. Now, if I'm looking at the determination of the area of surface generated about the y-axis. Okay. So again, we have for this particular item, so if I determine the area of surface about the y-axis, so once again I have between x is equal to 0 and x is equal to 2. So we have, first of all, if I put this in the context of integrating with respect to y, so we have y is equal to 2x, and putting this in terms of x equals, so I have x is equal to 1/2 of y, and we have, in the case of taking the derivative, okay, so I have dx over dy is equal to 1/2, and for the square of the derivative. Okay, so you have for dx over dy, quantity squared. Okay, that's going to be equal to 1/4. Okay, and at the same token, okay, so we have for x is equal to 0 and x is equal to 2. Again, we have y is equal to 2 times 0, which is 0. And for x is equal to 2, again, y is equal to 2x. And so we're going to have with, okay, the limits of integration. So I'm going from y is equal to 0 to y is equal to 4. And for the area of surface generated about the y-axis. So I'm going from y is equal to c to y is equal to d. And again, we have 2 pi times f of y. And I have times the square root of 1 plus the square of dx over dy, quantity squared, dy. And just putting in what I have specifically. So I'm going from y is equal to 0 to y is equal to 4. And we have 2 pi. Now f of y. Again, you had x was equal to 1/2 of y. And we have times the square root of 1 plus 1/4 dy. So we have here, so going from 0 to 4, and we have 2 times 1/2 is 1, and you have pi times y. And we have the square root of 5/4. Now for the square root of 5/4, I'm just going to mention 4 is a perfect square number. 5 is not. So I have going from 0 to 4. So square root of 4 is 2, so I can say that I have pi over 2 y times the square root of 5 dy. And we have upon following through, okay, so I have antiderivative of y is going to be y squared over 2, and we already have times pi over 2. So we're going to have pi y squared times the square root of 5 all over 4, as y goes from 0 to 4. And everything's going to be riding upon what we have in the upper limit. So 4 squared is 16, divided by 4 is 4. And so for the area of surface generated about the y-axis, okay, so that's going to end up at 4 pi times the square root of 5. Okay. And in the next case, I will show you what would happen if you integrated with respect to x.